Okay, so this is the second part of week 3, and we started with data preprocessing, but we are going to talk about this idea of dimensionality. Okay, so this is all from the first part. This is part 1. Sorry, I didn't stop at the right slide. Okay, so there's this thing in stats called the curse of dimensionality. And the curse of dimensionality effectively, I mean, in English, it means that when you have data that has a lot of variables, it becomes complicated. That really, in a nutshell, is what it's about. When you have a small number of variables, now small and big are arbitrary. I'd say like 20 variables kind of makes it a little big. Um, it's not uncommon, though, to have more than 20 variables. So when you have a lot of variables, the data has too many features. Features and variables are sort of interchangeable here. The curse of dimensionality is that the volume of the data space increases exponentially with the number of variables, leading to a sparse distribution of data points and making it difficult to analyze, visualize, and model the data accurately. Okay. Let's think about this in English, in sort of lower level. If you have data in one dimensions, you can just like plot it on a number line. That would be one variable. Like age, you can just do like a dot plot, which, I mean, dot plots are kind of like child's play in analytics, but you can literally take the data and just plot it on a number line. One way, not two dimensions. And then you learn your two-dimensional XY coordinate system. And you can also, oops, I spelled that wrong. I need to fix that because it bothers me. There. So, okay. That makes me happy, having fixed slides. Anyways, so you can plot in 3 dimensions, but then we have a problem. What about beyond 3 dimensions? Well, our little human heads and stuff, we can't do that. Like, we really can't see and touch and feel data beyond 3 dimensions because our world is 3-dimensional. I think every world is 3-dimensional. I don't know. It's hard to actually sort of understand how 4 variables would relate. And that's kind of what the curse of dimensionality means, is that it's difficult to analyze and model data accurately when you get into higher dimensions. Okay. And so effectively, our brains can't handle it. So we, quote, lose intuition. Human intuition understanding breakdown in high dimensional spaces, making it challenging to interpret and explain the results of models and analysis. Okay. Dimension reduction is the cure for this. Dimension reduction aims to reduce the number of dimensions in the data. And you're like, how do you do that? Hang on. It's not just like you have 10 variables and just using 2 of those variables. No, it's different than that. It's taking the 10 variables and creating derived variables that are not the original variables that capture the essence of what's in those 10 variables, but instead of having 10 variables, you have a fewer number. Okay? And so the goal is to reduce the dimensions of the data set, which is n dimensions, say 10, to k dimensions, which is, say, 3. Okay? I made this myself. Don't you like my graphs? This is an example of what we're talking about. So here is a graph in 2 dimensions. And if you notice carefully, I plotted them in 1 dimension. And the 1 dimension is still capturing a lot of the information. Like this is the lowest on the x. This is the middle one. And that's the higher one. So this is literally what we're talking about. And like this is the only way that I can understand this too. Is like we're taking data in a higher dimension and we're reducing it into a lower dimension. And that is what dimensionality reduction is all about. Okay. This, of course, only works with quantitative data. Categorical data, this is not an issue. Okay. You should always use normalized data for dimension reduction. You should actually, as a habit, whenever you're working with quantitative data in data mining, generally speaking, always normalize it. The only exception to that is if all of your data is on the same scale, which would be something like I'm working with grade data and it's all on a 0 to 100 scale. Otherwise, in general, you should always use standardized z-score data and not the original data when you're working in data mining. And remind me of that because I might forget. Okay. So how do we reduce dimension? What do we actually do? This actually is something that's learned in higher math, specifically like linear algebra gets into eigenvalues and decomposing things. So the mathematics behind this is a little bit above us, but there's something called principal components analysis. Okay. Dimension reduction is not just about removing variables. It's not that simple. It's common in fields that deal with large numbers of observations. I don't know that much about a lot of this stuff. I do know a bit about bioinformatics, but there's a lot of high dimensional data. It doesn't necessarily mean that the sample size n is the number of rows. The number of columns could be big. I mean, and sometimes you can have more columns than you have rows. So it's not really a matter of just like having a lot of data. It's a matter of having a lot of variables. Okay. Usually you would also have a lot of data, but not necessarily. Data mining is not just all about big data sets. And this is some biological thing that, I don't know, this is like organic chemistry stuff that I did take organic chem a long, long time ago. But anyway, so principal components are our main method of doing dimension reduction. And you're going to learn a little bit about these, and yes, we will actually do these. Okay. Principal components analysis breaks down n-dimension data into k-dimension data by creating transform variables. Okay. So you're like, what? We're going to take the original variables and we're going to make variables that capture the data in a smaller number of variables. Okay. New variables are called the principal components. They're basically, you can think of them as meta variables. They capture the essence and they turn out to be linear combinations of the original variables. And we're going to see this. Okay. Here is an example of this. Pay attention to this. So here is two-dimensional data, x and y, variable 1, variable 2, whatever you want to call them. The scatters of the original data. This line in the middle is not a regression line. It's what we're going to call a principal component, that you could actually make weights with these two and make these as a linear combination. And so the dimensionality reduction illustrated here is this one and this one are being reduced to this principal component. So you have two dimensions here, and you're reducing it to one dimension, which is along this one principal component. You can kind of think of it as rotating the axes around, but this is visually illustrating what a principal component is. It becomes a linear combination of the original two variables. And yes, it does look like a regression line, and it's very similar, but it's not a regression line. So effectively, this line here is capturing these two variables as a linear combination of these two variables, but it's a new variable. So you can be like, this could be like, I don't want to use y. Like PC, which is principal component, is a function of variable 1 and variable 2, and there's weights that you get on these two variables. There's a lot of mathematics behind this that we're skipping. Okay. However, you don't really need, and part of my challenge in this whole curriculum has been, like, data analytics used to be much more like graduate level stuff. And so, admittingly, the first time we ran some of these classes, some of the people, I had people teaching them, they were lovely people, but they were like PhD people, and they would teach them to our students like they were MIT researchers, and that didn't work out real well. So part of my challenge has been to take stuff like this and make it understandable to you guys. So I hope that's what I'm doing. But principal components is not, there's a lot of math behind it, but to actually understand the essence is not too crazy. Okay. So there is a data set called the cheese, and cheese tasting it's right here. So this is literally a cheese tasting party. So there's 20 cases of cheese. I think these are like different cheese samples. And these are like metrics: the acidity, the sulfuric acid, the lactic acid, and the taste. I don't know what the heck these are actually doing. I used this very data set for my very first graduate project in statistics a long time ago. So it's one of my little favorite data sets. But it's the cheese tasting data. These are just case numbers, but there's 4 variables, 1, 2, 3, 4, and all of them capture the taste of the cheese somehow. Okay. Okay, so even though there's only 4 variables, we need 6 plots to look at the 2x2 relation. So then what I did is I literally plotted each combination. You can see if you look at the acetic acid by the sulfuric acid, you get kind of a linear pattern going on there. If you look at lacid by acetic acid, you get that. So I'm taking each of these and I'm just doing, like, I plotted this to this, this to this, this to this. I'm doing all the bivariate relations. Because there's really no, the problem is this is 4 dimensions, which beyond 3 dimensions, there's really no way to look at. Even 3 dimensions is difficult. You can do an XYZ 3D plot, and you get like this data cloud, but you have to have a brain that's really visually intelligent to do that. It's hard, and there's just no way to represent four-dimensional data with everything on one plot. So you look at in terms of bivariate relations, and these are the first two, and then the second two, and then the third two. And you can see that all of these actually look a little bit similar. There's a lot of sort of weak linear patterns going on here. Okay. So notice that there's linear patterns in the bivariate scatter plots. They're not super great. They're not like a correlation of 1, but they're certainly there. I mean, you can certainly see that there's linear trends in all of these. Okay. So that actually makes it a good candidate for principal components, because what you're trying to do, you have 4 variables, but all 4 of the variables, when you relate them 2 by 2, there is this kind of consistency. And so that kind of indicates that they're sort of capturing similar information. So even though you have 4 variables here, it's possible that instead of using 4 variables, we can create a meta variable that captures what these variables are, and we can reduce the dimensionality from 4, okay, down. And so that's what I did. Okay. The 4 variables are somewhat redundant. They're a little bit collinear. They have similar patterns. They all appear to be conveying information about taste, which they are. Okay. So this is a candidate for dimension reduction. Okay. And so the goal of principal components is to get k principal components from n original variables. In this case, there's 4 original variables. So we could do k as 1, 2, 3, or 4. Typically, you don't want to go from 4 to 4, because the only thing you're doing then is just capturing your original data. Your idea, you want to reduce your dimension. Technically, you can do principal components analysis up to the number of original variables. But with 4 original informative regular variables, we can do, remember that principal components are creating derived variables from the original variables that capture information but reduce the dimensionality. So we want to do 1, 2, or 3. Okay. But how do you determine that? So k is the number of principal components, n is the number of variables. K should be less than n. You can technically do it equal to, but that's kind of ridiculous. But how do we actually determine k? And we've actually did this, if you took my 101 class, we did this when we did clusters. It's very similar. It's actually the same thing. So what you actually want to do is you want to do this thing called discrete plot. And what these are actually doing is capturing variance in the data. And there's a relation between capturing the variance and the information. The more variance you capture, variance, standard deviation, variability, whatever you want to call it, then you're capturing the information in that. The details that are a little hard to explain, but it works. Okay. So this right here, if you took my 101, you've actually seen this before. The orange curve is the one we want. The other one is just a cumulative plot of that. I didn't know how to take that off of there. So you're looking at this orange plot here, and this is a discrete plot. And what you look at when you look at a discrete plot, and this is the proportion of variability captured in each component. So one component would capture 70% of the variability. That's pretty good. Okay. And going back to this data, essentially what that's saying is 70% of the information could be captured by one variable. So we can take these 4 variables and we can capture that information, which is one variable. Usually, however, you don't want to do just one. So you look at the discrete plot and you look at where it elbows. So it elbows down here. Okay. So one variable captures about 70 and then an additional 12%. So these two combined are like 80%. That's what the cumulative does for you. So if you can capture 85% of the information in 2, that's good. Technically, you could go out to 3, but remember that you're trying to reduce the dimensionality. So going from 4 to 3, and you can see if you go from 4 to 4, then you capture all the variability, but you're creating the same number of principal components as you had variables, which is kind of a dumb thing to do. So 2 is actually our optimum, and when the discrete plot goes down, this is the 2. So that is our optimum. Our optimum number of principal components here would be 2. So that tells us that we can take these 4 variables and we can reduce it to 2 derived variables, and we can capture 85% of the data. Of the information. I mean, so you're sort of like, you'll lose out a little bit of information, but that's a good trade-off. Okay. So from the discrete plot, we're going to use 2 principal components. Okay. And the bend is this right here is the bend. Usually in most principal component plots, or discrete plots, there is kind of a nice obvious bend. Okay. So k equals 2 is a nice sharp bend. Okay. And so principal components are transform variables that are linear combinations of the old variables. or it should really say original variables. So for the cheese data, there's going to be two principal components. Again, I should have wrote out two. I'm going to fix that because it bothers me. Sorry. Okay. There, I'm happy now. You know what I mean? Okay. So the new principal, we're going to have two new variables, PC1 for principal component 1 and PC2. These are both going to be linear combinations of the original variables. Okay. Software will run this for us. Software will not typically determine the number of principal components. It will give you the scree plot, and then you typically have to enter the two as the number of principal components. But the software itself will calculate the rest for you, which is good. Which is why we also no longer really need to learn all the linear algebra and do all the details, because in the old days you have to sit there and actually do everything out by hand yourself. In the new days, you just know how to work the software and interpret it and know what you're doing, but you don't have to do all the calculations. So we're going to get two new derived variables that capture the essence of the original four variables. Software is going to run it. Okay. Oh my God, you're like, what? This is just, these four are just the original data. The data was a little longer than I showed in the first slide because I cut it off. This is just these guys again. It doesn't end at 21. I think it ends at 30. So the first, these columns, it's just the same data. This all is just the same original data. But then we have these two. These are our two new variables, PC1 and PC2. And then these are our old variables. So for the first cheese, I think these are like individual cheese samples. I have to admit, I don't remember. The first one had these specific values, and then you get these principal components. But there's a problem with this that you should have noticed. This one, oh no, actually there isn't a problem. I ran it correctly. This is not the normalized data. This is the original data, but the principal components were run on normalized data. Okay, so this here is the normalized data. I show you this down here. The principal components are fine. You get the same values. Okay, so you have now the two new variables, and each of these has a variable. So PC1 and PC2. You don't really need the original four variables anymore to work with this. You could do stuff like cluster analysis on the principal components now, which is one helpful thing to do, because if you ever remembered, well, we're going to do cluster analysis in here big time, but when you plot clusters, you do it on a two-dimensional plot. You can't work with all four variables. And then you actually can do it on the principal components. It comes out much nicer and cleaner. So these are the new principal component variables, and they have values. Where do these values come from? Okay. So the values come from, and this is the software. This is Orange. I wrote this curriculum so that I could use any software. In this case, it's Orange, but I could do this in Python and R and some other things too. But you get these things called weights, okay? Remember y equals mx plus b kind of stuff, the equation of line? This is very similar. It's not quite, okay? So from the software, you can get these. These are basically coefficients. Coefficients and weights, same thing. Pay attention to this. So for principal component 1, remember the principal components are derived variables from the original four. So you have 1, 2, 3, 4. You have the four original variables, and then you have these weights. These numbers, by the way, this 0.75 and that, that's these guys. They keep putting the percent of variance in there. And the reason they do that is because this one is like the more important one, and then there's this one. So they put the variance capture percent in there. But these numbers here that you can get from the software, these are the weights. So the way that you calculate principal component 1 is 0.46 times the acetic acid plus 0.51 times the sulfuric acid plus 0.50 times the lactic acid plus 0.51 times the taste. And you can literally calculate these guys from these guys, okay? Except not from this form. I actually left in here the original data. These are actually going to be calculated from the principal component data. I mean, from the standardized data, sorry. So the weights here that you can get from the software, this right here that we're looking at, this is a table of the weights. This is not the data. This is the data with the principal components in it. Okay. And then this is actually the data that's normalized. This is the original data. this is the normalized data. The principal components were done on the normalized data. So you can, and I actually did out here. So for PC1, for observation 1, which is negative 2.86, these are the weights from here, okay, for PC1. And I'm literally calculating the value of PC1 here, and this comes out to be negative 2.86. So I do 0.46 is the weight. Oops, that's the weight. So these are the weights. And then I just plug in the numbers. This number, I rounded a little because I was lazy. But when you plug everything in, you're going to get negative 2.86. And you can actually calculate the principal component. I could do the same thing for PC2, which would mean I would plug in, oops, sorry. These are the weights for PC2. And so I could do PC2 equals 0.85 times the CDIC plus point. And I could calculate that, and I would get this value here if I did that. But I didn't feel like doing all that basic math, so I didn't. But you can actually get the new derived variables pretty easily, and it's just basic. Once you get the weights, now this is what's hard to get. This is what you need the linear algebra to do. But once you have the weights, which are weights coefficients, same thing, then you can pretty easily just do the math and get these guys. But the software does it for you, so, okay. If you had done it on non-normalized values, no, I didn't, okay, you would get totally different values, okay. And you can see here, like, these are completely different numbers. You don't, in general, want to use non-normalized values for anything in data mining. So I don't even want to show you any more of that. Just always standardize your variables. That just makes your life so easy. You just do it. So now the cheese data can be thought of not in terms of the original four variables, but the two principal components. The trade-off is that we've captured 85% of the information. We did lose a little bit of information, but we made our lives a lot simpler because we can work with half the number of variables, which for things like plotting and clustering makes it a lot easier to work with. This is kind of an easy example, but I mean, what if you had 400 variables? Wouldn't it be nice to take 400 variables and capture them down to 5 variables? And that's what dimensionality reduction is all about. It's about taking data that has essentially too many variables for you to sort of like reasonably work with and making it simpler. Okay. Most of this course, we're going to actually use original data, but you have to keep in mind that anything that we do in this course, you can run it on the original data, but you can also run it on the principal components. And if you run it on principal components, because effectively principal components become derived variables that capture the essence of the variables, you can still do clustering and a whole bunch of stuff on principal components. So principal components are actually kind of like an important thing to at least basically understand. And they're not like super crazy hard. The only thing that's crazy hard is understanding how you get the weights and the linear algebra behind that. That's what's mathematically a little crazy. But conceptually, this idea of capturing variation and creating these derived variables is actually not too crazy. Okay. If you have a really large data set, it can be very helpful to run it on principal components, not the original data. So principal components are sort of like, they're literally derived from the original data, and you can use them as an alternative in a lot of analysis. Okay. How do you interpret them, and what do they mean? Okay. So when you look at the weights, now sometimes this is actually kind of hard to do because you have to understand the data in order to do this. So this data, though, isn't too bad. I mean, it's cheese tasting, right? So what do these things actually mean? Okay. So for the cheese data, if you look at the first one, look at the numbers here, 0.5. This actually looks like it's weighing all of these pretty simple. Remember, these are weights or coefficients. So 0.5, I mean, they're all almost around 0.5. So that first principal component is sort of like taking all of the cheese tasting information, weighing it equally. The second one is actually weighing the acetic acid heavily, and it's weighing against taste. So it's sort of a contrast type of thing going on there. Yeah. The interpretation may require like domain expertise, but you can kind of just, I mean, they do have meaning, and if you really know your data, you can actually like really explain what's going on here. I'm kind of faking it, but you know what I mean. This is, you can see the evenness of these weights, and you can see this one's really strong, so this is like capturing acetic acid, and these not as much. Okay. Don't be afraid to go back to, when you do work like principal components, don't be afraid. You know, if you're an analyst and somebody sent you like a big sales data and you don't necessarily understand what you get, analyze the data, come up with principal components, and then go back and have a talk with whoever like knows the data, but they might not know how to analyze the data, but they might like be the manager, like knows how the data was collected, and like what's in the store and what they're selling, and when transactions are recording, how they're recording, and what's being recorded, and what the different variables are. So don't be afraid to like call people up and like ask stuff, because they'll answer you most of the time. Okay. And that is the story of principal components. Again, they are, we have an original data. This is a relatively small one, but you could keep, if you had 100 variables, you can't work with 100 variables. I mean, you'll go crazy. You have to be able to take those 100 variables and capture the information in them in maybe 7 or 6, derived variables. So, principal components are particularly handy if you have a very large number of variables and you want to work with all the variables in some form. Like, you can't just work with part of them, and you have to reduce the dimensionality to something that's manageable. So principal components are actually something that is pretty kind of useful to know. Okay. And it's not too hard to do in the software. It was very hard to do before software, but in the software it's not hard. Okay. So there you go. That is week 3.